All right, thank you everyone for joining the MoldX 3D webinar series. This is the first webinar of the year, so I welcome you all to the new year, and with the new year comes a lot of new topics for the MoldX 3D webinar series here. The first one that we're going to be doing is this resolving pressure discrepancy issues in simulation. And this is actually a topic that has been very widely contested and very widely researched throughout different facets of the injection molding industry, as well as other types of industries out there, and different types of molding and all different types of parts. This is a very common topic for simulation guys to be discussing. All right, so the topics that we're going to be going over, first of all, what is sprue pressure? So maybe if anybody doesn't know what sprue pressure is, we're going to go over that for a little bit. Where can the sprue pressure discrepancies originate from? So what are the different causes? Where can we see these pressure discrepancies? How can we fix them? And some final remarks. All right, so let's jump right into it. What is sprue pressure? So sprue pressure is the reading from the melt entrance or from the pressure sensor, which is typically located around the nozzle. Usually, in other scenarios, you can actually get a reading directly from the screw itself. MoldX 3D uses solid mesh for all facets of the simulation, so anything that's modeled in MoldX 3D will be tied to this pressure drop as long as it's dealing with the melt system, that being the runner and the parts. So everything that's modeled in, there's going to be no approximations, there's going to be no adjustments, no assumptions or anything like that. The solid mesh is used directly to calculate the pressure drop through the system, that being, again, the runner and the part traditionally. All right, so everything after the melt entrance will begin to cause flow restrictions. So as the melt progresses through the melt system, the amount of pressure required to push that material forward increases, and that's where this sprue pressure comes from, or that's where this pressure curve that we're going to be talking about is going to come from. The restriction of flow will gradually increase the pressure requirement, like I mentioned. All significant regions of pressure loss should always be considered in the simulation. So this is actually a thematic statement that I'm going to be reiterating quite a few times throughout this webinar. Whenever we are looking at pressure differences, it's always important to make sure that everything is modeled into the software. The software can only calculate things that are included. It doesn't know what we want it to do intrinsically. All right, so going over the sprue pressure curve, this right here is a typical sprue pressure curve, just a couple of sections. The first one is the feed system. So traditionally we see a pretty large and quick increase in pressure in the feed system. This feed system will include the runner, the gate, the nozzle, and also the barrel. So basically everything leading up to the part geometry is going to be considered the feed system. Everything after this is going to be the pressure in the part, up until this peak. This pressure right here is typically where you get your values from if you've ever looked at a single value of pressure. This peak injection pressure or maximum injection pressure is a value which is typically given by most molding machines. This is typically the VP switch point, or the velocity to pressure transfer position. And we'll be talking about this in a little bit. After the VP switch, we drop down the pressure to our constant packing pressure. All right, so that's just a little bit about sprue pressure, just kind of what is it, and how can we evaluate the different sections. Also, throughout the duration of the filling through the parts, we're going to have these little spikes. These little spikes will indicate either when maybe when a weld line occurred, or where two melt fronts came together, or where an end of fill happened. These pressure spikes will actually give us a pretty good indication of where our flow imbalances lie. So whenever we have an imbalance of flow, these screw pressure spikes will be very prevalent. All right. So when we're talking about pressure discrepancy, typically we're talking about looking at the simulation, looking at what happened in reality, and in some cases you might actually see that the pressure between reality and simulation are maybe quite a bit different. So first of all, let's define pressure discrepancy a little bit closer. So discrepancies in our is always going to be looked at on a screw pressure curve. Now, I just mentioned a moment ago that there is a typical value that's output by most injection molding machines as either the peak screw pressure, peak injection pressure, maximum injection pressure. It's called a bunch of different things. But it's basically just the maximum value during the pressure, or I guess the maximum value of pressure during the injection stage. This is actually a very misleading value because it'll actually end up causing more questions than it'll give you answers at the end of the day. So one of the most important aspects, or one of the most important things that you want to get out of this webinar is that there's discrepancies. Whenever you see a difference between simulation and reality, you should always be looking at those discrepancies on a pressure curve rather than just looking at the last value. All right, there's three major zones for pressure verification. We actually just saw that in one of the previous slides there where we were looking at the screw pressure curve. There's the feed system, the part, and the VP switch to the end of fill. So these three sections, these three zones, are going to be what we use to identify what's the root cause of the pressure discrepancy. And looking at the slopes of the pressure curve through these zones is going to be the most crucial component of figuring out what's the pressure variance. All right, so I mentioned just a moment ago that there's, if I were to just look at the final points or these peak values, this case versus this case might actually end up seeming very similar. The values are a little bit different, but these actually might seem very similar if I didn't have a curve. If I'm just looking at the single point values, these might actually appear very similar, but we can see that they're quite a bit different. One of them diverges very close to the end, kind of towards the VP switch, and the other one here diverts very close to the beginning in the feed system. So being able to diagnose where these graphs are diverting and what section or what zone of our screw pressure curve is causing this discrepancy will give us a lot more information as to what we can do to fix this pressure difference. All right, so I'm going to start here in the feed system. So the feed system, again, is basically everything leading up to the part. So we have the runner, length, and diameter. So we want to make sure that those are modeled in correctly. We have the gate geometry. We want to make sure that that is modeled in as accurately as possible. We have the nozzle. I'll go into the nozzle in a little bit more detail for those of you that aren't aware of what a nozzle is. We'll go over that in just a moment. And then we have the barrel contribution. One thing about the barrel, I'm not going to go into it in this webinar. We actually do have another webinar topic specifically for compressibility in the barrel. And this pressure discrepancy due to the barrel geometry and due to the compressibility in the barrel is actually going to be included in that webinar. So I'm going to leave that out of this webinar, and you can join the barrel compressibility webinar, which will be a very, very, very interesting topic. It's something very, pretty much new to MoldX3D. All right, so the first topic here is the runner length and diameter. As far as the feed system is concerned, this is probably one of the most crucial components, making sure that your runner is defined accurately and completely. We can see 4 different scenarios. In this case, we have one with just a gate, one with a gate and a drop off of it. We have this one where we go all the way out to the melt entrance, and then the final one where we start to include some of the geometry as an annulus through the middle of the drop, which is kind of a volume subtraction for the valve pin. Over here on the right are the sprue pressure curves for each of those runs. We can actually see that the pressure drop, or I guess the sprue or the slope of the curve after the initial portion here is almost exactly the same. These lines are almost exactly parallel to one another. The pressure is increasing gradually, or I guess incrementally in this case. But the difference lies right at the beginning in the feed system section. And you can actually see how much of a difference we will have based on how much geometry we modeled in. With this orange curve, the orange curve represents just the gate. You can see as the pressure drop, or the difference between the pressure at the melt entrance and the pressure at the bottom of the gate, is very low in comparison to the other runs, which have much more volume and much more flow length to be considered. So if I'm running a simulation and I'm trying to compare the results from simulation to reality, I want to make sure that my entire runner system is modeled, not just a portion of it, because the pressure drop through the entire system is going to impact not only the sprue pressure curve, which is what we're focusing on here, but also the ability of the part to pack out and ultimately your warpage as well. So we want to make sure that our model is as complete as possible with all of the information that we need to give to make sure that the simulation is as close to reality as we can get it. All right, the next one here is the gate. So pressure discrepancy due to the gate is actually not as common as you might think. Flow resistance is typically linked to the cross-sectional area and flow length. So as the cross-sectional area decreases, the amount of flow restriction increases. As the flow length increases, the amount of pressure drop over that flow length also increases. So if our gate is not modeled inappropriately, if we have a different cross-sectional area, there's no way we can expect that the pressure drop through that gate is going to be accurate. All right, so we always want to make sure that the gate is modeled in appropriately. And here's just a very quick case study here, just to show you the difference between 2 different types of gates. This one here has a much larger cross-sectional area right at the part, but it actually has a longer flow length. You can actually see that the pressure drop through that is the blue curve is much larger than just having a nice simple edge gate. So the cross-sectional area for this edge gate is much smaller, but the flow length is shorter. So we can see that the flow length effect is kind of overthrowing that cross-sectional area effect. So both of those effects are actually very important, and we want to make sure that the geometry of our gate is always modeled in as accurately as possible. You can see that everything after the gate actually has the exact same contour, which means that we can isolate this pressure difference right around the gate. All right, the last one here is the nozzle. So as far as the feed system is concerned, the nozzle is typically as far up as we go. Like I mentioned, one of our future webinar topics will actually allow us to take the calculation up further into the barrel, but right now the nozzle is as far as we go. This over here on the left is kind of a traditional modeling procedure. So we have the part, we have a gate, we have the runner, but we traditionally actually want to include the nozzle that we're using in reality. So in order to inject the material into the part, you need to have some sort of nozzle geometry in order for that material to break off from between the cold runner and the machine. So this nozzle is actually going to cause flow restriction just like the runner does. And we always model this in with the same geometry that we have in reality and we model it in as a hot runner. You can actually see that the color here is orange, whereas the color here is blue. So we have a cold runner up all the way until the gate, and then this orange is a hot runner. So we'll kind of just include a couple of lines if you're using a line-defined geometry. You can also use a solid geometry for this in MoldX as well. You'll want to include the nozzle geometry on top of the sprue. And this nozzle can actually cause a pretty big impact on the overall pressure drop through the system. So this is actually a real case. This is a case study that we did last year. And we actually have the nozzle geometry right here. You can see that there's a very, very narrow nozzle geometry, and it actually gets very, very narrow as we get closer to the sprue. As far as the sprue pressure is concerned, we have three sections, or I guess three main sections that I'll focus on. We have the nozzle, we have the sprue pressure, we have the sprue and runner sections, and then we have the part. If we overlay those, on top of one another, then we can see that actually this red one here is the one from reality. If we overlay the curve from the machine onto the MoldX 3D sprue pressure curve, we can actually see that there's a very, very large difference between this red curve, which was the original simulation. The other ones here are just a couple of iterations that we made. But the difference seems actually quite large. What we ended up doing in this case is we just isolated that one curve, and then we overlaid it onto the sprue pressure curve from reality. We can actually see that the slope of the sprue pressure curve, although it's not perfect, and it rarely ever will be perfect just because there's some environmental imperfections that we can't really take into consideration, but you can actually see that the slopes are relatively the same through the part and the runner. That means that we can isolate this pressure discrepancy. You can this right here lined up pretty much with this up here. So it's really just this slope that was causing this large amount of pressure drop. And in this case, it actually ended up being the nozzle. Once we included the nozzle, we got this red curve. And once we got a little bit more information on the nozzle, the kind of like the real geometry that we saw in that first slide, then we actually got up closer to where this green curve is. We can see that this is much, much closer to reality. You can see that that initial pressure drop caused almost completely by the nozzle. So this nozzle can actually be very, very impactful, and you always want to make sure that you're modeling in the nozzle if you have that information available to you. If you're a part designer, or if you maybe if you don't have that information, then you can use past experiences to give you some sort of indication as to what nozzle is going to be used. But I would recommend using a nozzle to run the simulation to make sure that the pressure prediction is as accurate as it can be. All right, so moving on to the part, there's a couple of things that we need to talk about when it comes to pressure discrepancy in the part. And both of those are typically going to be tied to the gate location. So making sure that the location of the gate is exactly the same between simulation and reality is extremely important, because the location of the gate is going to impact the flow length, which I just mentioned with the gate and the runner. If our flow length is different from reality, the pressure drop is going to be different, and that's a huge problem. The other thing is flow balance. So making sure that the location of our gate is going to severely impact the balance of our flow, how we can get the material to the end of fill regions more or less at the same time. All right. So let's look at flow length. So as flow length increases, the resistance to flow increases. So as the material starts to move through our part, the amount of pressure required to push that material forward increases. So if my gate is not placed correctly, maybe if my gate is placed a little bit over to the left, then actually my overall flow length is shorter on this side, but much longer on the right side. And if the flow length is longer, pressure requirement's going to be higher. And if I'm trying to compare between simulation and reality and my gate location is not the same, then I can definitely expect there to be a difference in pressure for my part. As far as flow balance is concerned, flow balance is basically just the ability to get the material to the end of fill region at more or less the same time. So if we have a balanced flow in simulation and we go to reality and our flow is not balanced, then we can expect there to be not only a difference in the flow length, but there can actually be dangerous pressure spikes right at the end of fill. With that. So in this case, we have a kind of like it appears to be a center gated part. It looks like it's geometrically centered. But we can actually see as we get towards the end of fill to 85, 90, and 95%, we can see that one side fills much faster than the other. Pressure spikes like this are caused because the material has nowhere to go on one side of the part, so it has to very rapidly shift to going in the other direction. And that is a pressure phenomenon, a pressure-based phenomenon. We call it momentum. These momentum shifts are what's going to cause this pressure spike, and if these pressure spikes are at the end of fill, you'll actually see a very different peak pressure than what you might be seeing in reality, or vice versa. All right, and one interesting tool that you can use is overlaying the sprue pressure plot on top of your filling animation. So making sure that your flow balance is as good as possible, or at least that your flow balance is what it is like in reality. This ability to overlay the sprue pressure on top of the melt front is going to be very important. All right. The third region of our sprue pressure curve is switched to the end of fill. So at the peak pressure, the maximum pressure typically, we have a phenomenon which we call the VP switch. This is where we're basically switching from our filling stage, which is in the velocity control, to pressure control, or the packing stage. So we're basically switching from filling to packing maybe like 4 or 5% volume percent sooner than when the material gets to the end of fill. And this is just to give our machine a little bit of a transition time so that we're not trying to switch immediately when we get to the packing stage. All right, this VP transfer position or this VP switch point is very important to match between simulation and reality. If I'm looking at a sprue pressure curve and I'm looking at an x-axis of time, I want to make sure that my VP switch point is at exactly the same time as we have in reality. If I were to overlay these two, I would want to make sure that these peak points or these maximum points are at the same time. You can actually see in this case how two different VP switch points yield very, very different peak sprue pressures. You can see that all the way up until this point, the sprue pressure curves are exactly the same. It's just when we delay the VP switch by another 4%, you can see that the pressure has to increase much, much more. And this can be actually a very big problem. Even a difference of maybe 0.5% or even a difference of 0.1 seconds can cause a very big difference in the maximum pressure that you're seeing between simulation and reality. So this VP switch point is actually very important to make sure that you're having this switch happen at the same between simulation and reality. All right. How can we fix sprue pressure discrepancies? So we have a systematic method to identify what the root causes of sprue pressure discrepancy would be. The first one is to obtain a sprue pressure curve. This is a very important step. Making sure that you have a sprue pressure curve on hand from your machine is extremely important. Then you want to compare that sprue pressure curve to the simulation pressure curve. After you do that, you'll look for pressure spikes and ensure that the timings are similar. Look at the VP switch point especially to make sure that the time is similar for the VP switch. And then finally, looking for some potential environmental variables that might impact the simulation that we can't really account for. Some of those environmental variables might include inaccuracy of the mold cutting, mold surface defects, so maybe like a scratch, or maybe the roughness of the surface is a little bit different, or maybe it's a little older of a mold. Homogeneity of the melt before the modeled system. So in the barrel, when we're looking at I guess the simulation just assumes that we have a nice uniform temperature as we come into the system. If our barrel isn't long enough to obtain some sort of homogeneous melt, then there's always going to be some sort of discrepancies as far as the pressure requirements to push that material if the viscosity isn't the same between the material there and what we're simulating. Moisture in the pellet, so if it's a humid day or if your dryer isn't working properly or efficiently, then you might actually see a difference in the simulation results versus reality. Fiber breakage is actually something that we can simulate, but it is a complex phenomenon that might not be always accounted for. And then finally, compressibility in the barrel, which is, like I mentioned before, is going to be a separate webinar topic that you guys can look out for. All right. So conclusions, it's always easy to just take the maximum value between simulation and reality. Your machine will give you the peak injection pressure, and you can find the peak injection pressure from simulation. You can compare those two. That's actually going to just lead to more questions than answers. There's nothing that you can really get out of a single point value besides just saying that, okay, the simulation isn't doing what it's supposed to, or maybe I don't have everything modeled in correctly. You always want to make sure that you have the sprue pressure curve that'll allow you to diagnose the true cause of any pressure discrepancies. And one last note here, although the simulation is getting more and more accurate, as we imply more more advanced information into the computation, there will always be some sort of unpredictable variables that will throw off the simulation results from the real molding process. And it's important to keep that in mind. The simulation will typically never be 100% correct. There will always be some sort of variables that we need to make sure that we keep in mind, at least.